Good day, everyone. Last meeting, we have learned about definitions and properties of numbers and sequences. And also, we have acquired the concepts of sums and products of integers. Now, let's unravel the powerful proof technique for finite numbers, which is the principle of mathematical induction. This is Clarabel Siayanan, and I am your reporter for today's discussion. The theory of numbers is concerned, at least in its elementary aspects, with properties of the integers and more particularly with the positive integers 1, 2, 3, and so on, also known as the natural numbers. These natural numbers have been known to us for so long that even in a younger age, we are very oriented with these numbers. And as mathematician Leopold Kronecker once remarked, God created the natural numbers, and all the rest is the work of man. This suggests that natural numbers are independent of human thought and discovery of mathematical concepts. Some mathematical concepts include well-ordering principle and mathematical induction. Well-ordering principle stated that every non-empty set S of non-negative integers contains a least element. That is, there is some integer a in S such that a is less than or equal to b for all b's belonging to S. This suggests that for every non-empty set S of positive integers, there is a minimum or least element among all elements in set S. Example: set A containing integers greater than 10 in which 11 as least element. And if there is a least element in that non-empty set, then the set is well-ordered. With the well-ordering principle available, it is an easy matter to derive the first principle of finite induction, which provides a basis for a method of proof called mathematical induction. Mathematical induction. It is one of the fundamental methods of writing proofs, and it is used to prove a given statement about any well-organized set. In mathematical induction, it is used to prove well-ordered set. However, if the set is not well-ordered, then we cannot make use of mathematical induction. It is also a technique that is used to prove the basic theorems in mathematics, which involve the solution up to n finite natural terms. And the principle of mathematical induction is sometimes referred to as PMI. According from the book of David Burton entitled Number Theory, 7th edition, in which the theorem of 1.2 pertains to the principle of mathematical induction, it stated, let S be a set of positive integers with the following properties. First, the integer 1 belongs to S, and second, whenever the integer k is in S, the next integer k plus 1 must also be in S. If the two properties are satisfied, therefore we can say that the set S is the set of all positive integers. The idea of mathematical induction can be compared to falling dominoes. When a domino falls, it knocks down the next domino in succession. The first domino knocks down the second one. The second one knocks down the third one, and so on. In the end, all of the dominoes will be bowled over. Similarly, we need to prove if the statement for n equals 1 is true, and that is our base step. And if it satisfies the base step, then it is possible that the statement is true for some other values of n, say n equals 2, n equals 3, and others. So we assume that S of k is true for some n equals k, and this is our assumption step. After the assumption that the statement is true for S of k, we now prove that S of k plus 1 is true, and this is our induction step. And if S of k plus 1 is proven to be true, then we say that the set is true for all elements of our natural numbers. Now, let's prove the principle of mathematical induction. So first, we assume that the first property belongs to S. In other words, integer 1 belongs to S. And we need to prove, kay since 1 belongs to S naman, so therefore we need to prove that the k plus 1 must also be in S. So we start our proof by letting a set in which this set is a set of positive integers not in S. So T is not a subset of S, and we assume that T is non-empty. Kay T is non-empty and it is a set of all positive integers not in S man, so we can say that this T is well-ordered. So by well-ordering principle, T possesses a least element, and we don't know what that element yet, so we denote the least element by A. So again, A is the least element of our set T. And uh, balik ta sa itong assumption that 1 is in S, so basically, A is greater than 1. Kay 1 is an S man, and A is the least element of our T, and this both are positive integers, and trivially 1 is the smallest element of positive integers, so we can say that the smallest element in T is greater than 1. And so kung minusan pa gyud nato ning smallest element ni A by 1, that is greater than 0 kay we're talking about positive integers, but less than the least element of our T. I hope na-gets ra ni, no? So kung mag-minus tag 1 atong least element ni A, so we can say that the number still is greater than 0, but it is lesser than A. So the choice of A is the smallest positive integer in T implies that A minus 1 is not a member of T. Kay A man, no? A man is the least element, so the other element A minus 1 is not in T. So it can be in S. Or equivalently, that A minus 1 belongs to S. So that's what I have said. So by hypothesis number 2, S must also contain katong next na integer k plus 1. So we have the element of S nga A minus 1, and the next integer of A minus 1 is A minus 1 plus 1, which just equal to A. So this contradicts the fact that A lies in T. Kay diba, dapat ma-prove nato nga ang K plus 1 must also be in S. Since our A minus 1, I hope naka-follow, since our A minus 1 is in S, so the next integer should be in S. However, ang atong na-solve is the least element of T, and T and S kay wala sila common, no? In other words, mutually exclusive si set T and si set S. So this contradicts the fact that our A lies to T. So we can say that T is equal to empty set and S contains all positive integers, and that is the end of the proof. So this proof uses the proof of contradiction, in which it is impossible for K plus 1 to not be in S. Now, let's prove some statements using the mathematical induction. So for example number 1, for each n element of natural numbers, the sum of the first n natural numbers is given by 1 plus 2 plus 3 plus n is equal to the 1/2 of the product of n and n plus 1. Now, let's prove this statement using mathematical induction. So, as what I have discussed, there are three steps under mathematical induction. First, ipakita natong B step, in which true atong statement for n equals 1. And then if true atong statement for n equals 1, then we can proceed to the second step, which is the assumption step. And after nato nihimog assumption, we need to show that the next integer of our k, which is k plus 1, should also be in S, and that is our induction step. So if the base step pa lang daan, or di na or false na statement, no, pag n equals 1, therefore di na nato siya i-prove. So murag kuan lang siya kanang proof using counter example. Pero in proving this one, di man magbuang man tag pumangita og counter example, so we need to prove this one kay bisag ipampuli pa na nimo possible numbers of n dira equal gid siya, no? So the point is we cannot show all the values of n by substituting the values of n here. I hope na nakano by substituting all the values of n, kay n is infinite man. So that's why we need to make use of a method, and that is the mathematical induction. So first we let S now be a set of natural numbers satisfying the given statement. So 1 plus 2 plus 3 plus n is equal to 1/2 times n plus 1. So for the base step, no, by the principle of mathematical induction, for n equals 1, we have 1 as natural number is equal to 1/2. Ipuli din nato ning kung unsa atong n nga value of n. So we have 1/2 of 1 times 1 plus 1, that is equal to 1, no? Copy, is equal to 1 plus 1 is 2 times 1, that is 2, and 1/2 of 2 is 1. So this satisfies the given equation, thus we can say that 1 is in S. So I hope naka-follow na. And actually we can, after nato napakita nga true atong statement for n equals 1, pwede nata mo dito sa sa assumption step. But based akong naandan, mangita pa ko another value of n which satisfies the given statement. So for this, I use n equals 2, and then gitry na ko sa 2. So 1 plus 2, kay 2 man atong natural number, is equal to 1/2 of n, which is 2 times 2 plus 1. 2 plus 1 is 3 times 2, that is 6, and 1/2 of 6 is 3. So it satisfies the given statement. Thus we can say that the n here nga 2 belongs to S. So this is our base step. Again, pwede ra nga dili nang mangitag another value of n. You can actually cut off here na, no, kaning sa n equals 1, basta kay napakita ninyo nga n equals 1 is true for that statement. So the idea here nga nang nangita pa kog lain na value kay in the assumption man good, we need to assume that there is another number, no, that is na siya another values of n which satisfy the given statement, another value or some values of n that satisfies the given statement. So in the assumption, let's say nga katong mga values of n nga mo satisfy sa ato ang given statement, tawagon na to as k, which is greater than or equal to 1, since we're dealing with natural numbers. So we have 1 plus 2 plus 3 plus k is equal to 1/2 times k plus 1, and this is our assumption step. Again, we assume here that this statement, kay since nakuan siya sa base step nga n equals 1, so there are some values of n, let's say that some values of n, tawagon na to k, nga mo satisfy siya sa given statement. So we're done with the base step, which is here, and then we assume na nga for k, some k greater than 1 or equal to 1, we have this 1 plus 2 plus 3 nga statement. Next is the induction step. So, in the induction step, diba, we need to prove that the next integer k plus 1 should also be in S. Before na to maingon nga ang set S nato is just equivalent to the natural numbers. Okay, so again, this is our assumption step, in which we assume that for some values of n, let's say that k is equal to 1/2 of k times k plus 1, or it satisfies the given statement. So given here, ang ato magud i-prove is the next integer of k, which is k plus 1, iyarang isatisfy ang atong given statement. So, if we're going to add here, no, kay addition man ni, sum man ni siya of k and plus the next integer of k, which is k plus 1, that is just the same by having 1/2 of k times k plus 1 plus this next integer. No, kay sum man siya. And then, by manipulating this side, we have k times k plus 1, that is k squared plus k, and then plus k plus 1. And by operating, we have 1/2 of k squared plus k plus 2k plus 2, that is having the same na LCD. So we have 1/2 times k squared plus k plus 2k plus 2. So combining like terms, we have 1/2 of k squared k plus 2k, that is 3k plus 2. Okay, so we have k squared plus 3k plus 2, and note that this k squared plus 3k plus 2 can be factored out into two factors. We have k plus 1 times k plus 2. Again, if we can actually represent the sum into this form, therefore we can say that k plus 1 is an S. So by just looking at the form here, kaniyang ato ang guide, no, 1/2 of the n times n plus 1. Ang dapat end na result kay mag-plus naman ka diri k plus 1, dapat ang kaning mga n mapulihan ni k plus 1. Mo gyud na ato ang final na result. So therefore, we have here 1/2 of k plus 1 here sa n times k plus 1 plus 1, which really satisfies the given statement. In other words, we can say that this k plus 1 here is also an element of our S. So therefore, we can say that S is just equal to the all positive integers or all natural numbers by showing that this one for all n in our elements of natural numbers. And that is the end of the proof. Supposed to be na siya sa ubos. So we have successfully now proved the first example. So now let's have another example. So example number 2, we need to prove that 1 times 2 plus 2 times 3 plus 3 times 4 plus so on until n times n plus 1 is equal to 1/3 of n times n plus 1 times n plus 2 for all n greater than or equal to 1. Okay, so here, no, actually we can make use of the principle of mathematical induction, kay since this n natural number nato kay infinite magud ni siya, so we cannot just, as what I have said, we cannot just substitute all possible values of n tapos ipakita nato nga satisfied siya for all n, no, which is an element of natural numbers. That's why we need to make use of another method, which is the principle of mathematical induction. So first, we let S be a set of natural numbers satisfying this statement. So for the base step, diba, tulad ako process, or steps, I mean, the base step, the assumption step, and the induction step. So for the base step, ipakita nato na this statement is true for n equals 1. So for n equals 1, we have 1 times 2, no? 1 times 2 is equal to 1/3 times 1 times 1 plus 1 times 1 plus 2. And 1 plus 1 is 2 times 1 plus 2, that is 3. 3 times 2 is 6 times 1, that is 6. And 1/3 of this is 2, which satisfies the given statement, no? Or the given equation. Thus, we can say that 1 is in S. Again, pwede na ta mo proceed sa atong assumption step if napakita na nato nga ang n equals 1 is true for this statement. But ako nag-include na sad kog another value of n, which is akong gi-include si 2, n equals 2, akong gitan-aw if it really satisfies the given statement, no? So we have 1 times 2 plus 2 times 3, kay up to 2 natural numbers man ta, so diri lang tataman. And then we substitute there, no, that the value of n. We have 1/3 times 2 times 2 plus 1 times 2 plus 2. So we have 2 plus 1, 3 times kaning part is 4, 12 times 2, that is 24, and 1/3 of 24 is 8. So therefore, it satisfies the given equation. Thus, we can say that 2 is an element of S. So we're done with the base step. Now, let's go to the assumption nato step, which is kaning part. Okay? So, naa may values of n nga mo satisfy sa given equation, but we cannot tell if all values of n mo satisfy siya sa given equation. That's why we assume, no, that for some values of n, let's say that value of n na k greater than or equal to 1 is satisfies the given statement. So we have 1 times 2 plus 2 times 3 plus 3 times 4 plus and so on, plus k times k plus 1 is equal to 1/3, no, times k plus 1 times k plus 2. So we're done with the base step. This is our assumption step. The next one, unsa gito the third one? Yes, proceed na din ta sa ato ang induction step, in which kay k man is true sa ato ang given statement, we need to prove that k plus 1, or the next integer of our k, should also be true in our statement. So again, we copy this one, no, kay kaniman atong true nga statement, lungagan lang nato atong next niyang integer. Remember that the next integer is expressed as k times is expressed as k times k plus 1. So, kung atong next integer kay k plus 1, ato siya ibalik. So, we have k here. So, mahimo siyang k plus 1 times k plus 1. Atong k, mahimong k plus 1. So, we have k plus 1 plus 1, and that is k plus 2. So, kay plus man to diri o katong next integer, diri og next integer, so mag-plus pud ta diri og katong atong gi-plus here para balance ang atong equation. So we have 1/3 of k times k plus 1 times k plus 2 plus k plus 1 times k plus 2. So dapat i-bear na to sa atong mind nga dapat ang result should be expressed like this, in which mapulihan lang ng n by k plus 1. Okay? So manipulating this side, we have 1/3 of k times k plus 1 times k plus 2 plus k plus 1 times k plus 2. And having the same, no, ang sitag ani denominator 3, so ang ato ang new expression, we have k times k plus 1 times k plus 2 plus that is 3 times k plus 1 times k plus 2. Note that k plus 1 and k plus 2 are common in these terms, no? Kaning k times k plus 1 times k plus 2, and sa 3 times k plus 1 times k plus 2. So we can factor the common factors here, which is k plus 1 and k plus 2. So we have k plus 1 times k plus 2 times, i-factor out na to siya kaning nga term, ang mabilin is k now. So we have k, and then atong igawasang k plus 1 o k plus 2, mabilin is k plus 3, which is over 1/3. So we have this, we have this, sorry, pangit. Tata erase. We have this, final, no, the 1/3 of these factors. And note that we can actually rewrite this one into this na. So 1/3 of k plus 1 times k plus 2 times k plus 3. Or in other words, we can have 1/3 of the ang butog maklaro ra ninyo. Diri 1/3 of the k plus 1, pagyan na to ang n of k plus 1 times k plus 1 plus 1, that is k plus 2, and times k plus 2 ay k plus 1 plus 2, that is k plus 3, which satisfies the given statement. Thus, we can say that since our k plus 1 is an S, we can say that this statement is true for all n greater than or equal to 1. I hope wala kayo kung anong problem. If may problem, actually, you can just message me if mali akong explanation or wala ninyo na-get sa akong explanation. Sige. So, as what I have said, we have here, no? Actually, discuss na ako. As what I have said, we have here, in which we can express this kani in terms of k plus 1. So we show that k plus 1 is n s, and therefore this statement is true for all n in our natural numbers. That is the end of the proof. So, if may questions, you can actually message me sa akong Facebook na account, or pwede ra mangutana sa ako personally if kailata sa personal. No? So, I think you're ready na to have the practice test. So, I prepared 3 practice tests to work on. First, for all n greater than 1, prove that 1 squared plus 2 squared plus 3 squared up to n squared is equal to the product of n times n plus 1 and 2n plus 1 all over 6. And for number 2, for all n greater than or equal to 1, prove that the sum 1 plus 3 plus 5 plus up to 2n minus 1 is equal to n squared. And for any positive integer number n, prove that n cubed plus 2n is always divisible by 3. So if you have questions regarding these practice tests, pwede ra mong PM sa ako and ato siyang i-check, no, or ato siyang tabangan og solve. Actually, I prepared ako the solution for this. So pwede ra ko ninyo i-chat sa solution ani. So again, thank you for listening. I hope na mo na-learn from this discussion, and I hope nakita ninyo ang value, specifically in proving statements. So that's it. Thank you for listening, and see you around.